So each electrode half cell has its own electric potential based on what metal it is relative to the hydrogen standard. So then when I want to put these two things together, I can look at the actual difference between the two half cells, right? 0 was just relative for each side. Newest convention, reduction happens at the right. Draw your pictures this way. Think of everything in this way so that you don't mess up your signs, okay? So when you're trying to get the difference in electric potential for your cell, here is your battery, your electrochemical cell. Always do reduction minus oxidation. Do the right side minus the left side. This is literally how it's shown in your book, right minus left. Okay, so reductions at the right, reduction minus oxidation. The other way to maybe write it, cathode minus anode, whatever you want to do to make sure your signs stay correct. Okay? So up next, we have a practice problem. Okay, so we're going to jot this down quickly. You're given the following two reactions. Note, these are both standard reduction potentials. They're both written as reduction right now. Obviously, one of them isn't going to get reduced, okay? So this isn't the direction for both of these reactions. Given the following two reactions, you want to make a battery out of copper and silver, okay? Write a balanced chemical reaction for this battery. Illustrate the electrochemical cell. Be sure to label the diagram completely, designating the direction that the electrons are flowing, which one's the anode, which one's the cathode. We don't really have time so much. Last time I had people come to the board and draw it last semester, which they did a really good job. It was really well done. Identify the oxidizing agent and reducing agent, okay? So this is some new terminology. Oxidizing agent, a substance that tends to bring about oxidation by being reduced and gaining electrons, okay? So it's the thing that gets oxidized. The oxidizing agent is the thing that gets reduced, causes oxidation of the other thing. And reducing agent is then the reverse of that. What is the standard electrode potential difference of your battery? So take a couple seconds and work on this one. Maybe I will just... I encourage you to talk to whoever's sitting around you to, speed your process along, work together.
So do you multiply? You don't multiply this way. You just everything. So you multiply the so you reagents. No, you don't. No, you don't. We don't. Why? You don't. It's just not the bottom. You don't. You don't.
You don't. Okay, so let's talk about this one quickly. So I'm trying to make a copper-silver battery. I was given standard reduction potentials for reduction of copper and silver relative, like I said, to a standard for each of these half reactions. Part A was to write a balanced chemical reaction for your battery, but the first thing I want you to do in order to write sort of this balanced reaction is think about which one would rather get reduced, which one wants to receive electrons. So what was the answer to this? Which of these two is getting reduced? Silver. How did you decide? It's higher on the table. It's more positive, okay? On our standard potential table. The one that is more positive will be higher up. If I didn't give you these values, how would you have gotten them? I'd go to the table and get them. Use the tables from the textbook. I will give them to you, but don't use ones from the internet in case they're slightly different and then your numbers are slightly different and you'll be given table 10, 11. You would just go look them up, okay? Great. So then that means that copper gets oxidized. Is getting oxidized. So I can write each of my half reactions here. I have silver getting reduced. Okay. And then I have now copper is getting oxidized. In order to balance these things, I want my electrons to drop out on each side. I'm going to multiply this top part by 2. And when I add these two things together, I'm going to have 2 Ag plus. This is sort of aqueous silver plus solid copper is going to solid silver and aqueous copper. Okay. So again, if you're asked to write a balanced reaction, this is what I want you to do. I don't want the electrons in it. B was draw a picture. So again, use convention. What should I draw on the right side? The right side is my reduction reaction. The right side is my cathode, however you want to memorize it. So this bar here is silver, okay? And like I said, it's in some solution, maybe nitrates or what are floating around. Okay? And then on this side, I can have a bar of copper. Okay? This is anode. This is oxidation. They're connected somehow. And I have electrons flowing. What else is my picture missing so the current keeps flowing? A salt bridge, yay. All right, this is the direction of flow of my NaO3, okay. Salt bridge. What's my reducing agent? I am what reduces something else. Solid copper. What is my oxidizing agent? I'm the thing getting reduced. Aqueous silver. And for part D, I was asked for the difference. Difference means delta for my electrochemical cell, for my battery. One way to do this, the right side minus the left side, cathode minus anode. Okay. So I'm going to have positive 0.8 volts minus positive 0.34 volts equals plus 0.46 volts. Is this what people got? Okay. The other way to do this, if you want, it is totally up to you. When I flip the direction of this reaction up here, it would flip my standard potential. This is written as a standard reduction potential. If I flip it to oxidation, the sign flips. It's now negative 0.34 volts. If it's now written as an oxidation reaction. Okay? The same way every other reaction I've ever written, I said, oh, if the delta G for this reaction was spontaneous, that means the other way is non-spontaneous, and go ahead and flip the sign. The same thing is true here. And so if you are, because some people like just wouldn't listen to me and just stick to the convention the whole time so your signs don't mess up. If you want to do it like this, then you can think of it like addition. I'm adding what's going on with equation 1. I'm adding what's going on with equation 2. And then what you have, this would be, this is sort of like I said, maybe an extension of Hess's law if you want to. That was for formation and for enthalpy. But again, I can just sum things up if that helps you. This would be reduction reaction plus the oxidation reaction. So then what I have is positive 0.8 volts plus a negative 0.34 volts once I flipped it to an oxidation reaction. And this will also give you, your answer will still be the same if you did it right. I don't know where people learned it that way instead. I had an issue last semester, just people wouldn't listen and do this. So mind your signs, because you'll be penalized if you do it wrong. Okay. Ta-da! My drawing looks exactly like this. Super perfect. So I have my copper nitrate solution, and I have my copper in it, and then I have a silver nitrate solution over here, and I have my silver anode in it, and it's beautiful. Okay? And I have a voltmeter telling me my answer.